Okay, Markus, please, stage is yours.
Yeah, thank you very much, and thanks for everybody who sticked to the coming to the talks. It was a great pleasure for me to try to explain some of the things we do in this big project. So remember that, so I suppose by now my thing froze again. I'm sorry. Let's get it back. Okay, good old tradition. So last time we essentially arrived at a point saying that if we take a ring with global dimension 1, so for the rest of the talk, then statement is the genuine symmetric L groups, so the L groups associated to this genuine symmetric Poincare structure are either the quadratic L groups, so the ones associated to the quadratic structure, or the symmetric one, depending on the n, so the degree in which we are. So for n less or equals to -3, there are quadratic L groups, and for n greater equals to -2, there are symmetric L groups. For this to be absolutely correct, maybe we should assume that the fraction field of R in this case is not of characteristic 2. So with this information, what remains to be done today is to calculate symmetric and quadratic L groups of Dedekind rings whose fraction field has some nice properties. So that is essentially what I want to explain today, how we can get our hands on these symmetric and quadratic L groups. And so step 1 is the symmetric case. So in other words, we want to first calculate the symmetric L groups. And okay, so the setup we want to employ here is as follows. So we fix a Dedekind ring and let S be a collection of non-zero prime ideals of our ring. That, so yeah, we just fix a collection of such non-zero prime ideals. And then we define a ring that I want to call R subscript S in a rather ad hoc manner. So we just look at the collection of all elements in the quotient field K, whose p-adic valuation is non-zero, is non-negative if P is not contained in S. Okay, so I have to say a couple of things. It turns out that if you have a Dedekind ring and you localize at a prime ideal, this is a complete, no, it's a discrete valuation ring. That is a fact from algebra. So what happens is that this discrete valuation on this discrete valuation ring extends uniquely to the fraction field K and determines just a discrete valuation on K. And so we can ask whether or not this discrete valuation associated to a particular prime on an element in your field is greater or equals to 0. And concretely, if you think in terms of, fractions R divided by R prime, then essentially you just want to have control in what sort of prime elements R prime can lie. I mean, we're just saying that certain the denominators in our fractions have a certain control given by the primes that we have. This is just a general construction one can do. Turns out always to be a Dedekind ring again, and the most important examples for today are the following 3 kind, which are much easier to grasp. Namely, if S is the collection of all non-zero primes, then this ring is just the fraction field, right? There's no condition left, so this is just the fraction field. Conversely, if T is a multiplicative subset of R, you can construct a collection of prime ideals, all those which intersect this subset T in a non-empty manner. And then this localization, this R sub S is going to be just given by inverting our set of elements T. And as a special case of that, for instance, if you let S be the collection of some prime numbers P1, some primes P1 up to Pn, say, and you assume that there exists numbers Ri such that this product of prime ideals turns out to be principal, then this ring Rs is just given by inverting that particular element X. So in other words, a Dedekind ring is a ring in which every ideal is uniquely written as products of powers of the prime ideals in your ring. And so you can imagine that whenever you have an element X, there will be such an expression. So then you just collect all these primes together, and this slightly more general construction will then reproduce R joint 1 over X. Okay. And okay, I mean, this is just the setup that we want to choose, but it's not particularly important for today. I just want to advertise that yeah, one can do these constructions in this generality. turns out that this ring RS is not in general given by inverting a couple of elements in R. It's some other ring, but in many special cases, it is given by inverting a set of elements, namely in these cases. Okay, it's just a general construction we can do. Slightly ad hoc, I agree, but okay. So the proposition that we first want to prove, that is something that was asked also yesterday in the exercise session, is about localization sequences in L theory, for that matter. And the proposition that that we want to show is that the extension of scalar functors, so there's a ring map from R to RS, of course, and that we can base change along this ring map. So we obtain this from the of R to that of RS, and this extends to the projection of the Poincare-Verdier sequence of this kind. So this is this projection of Poincare-Verdier sequences, where this term is just defined to be the kernel. Okay, I mean, we just say that is the full subcategory on this Poincare infinity category on all objects which map to 0, and we just restrict the Poincare structure to this full subcategory. That is well defined because this functor turns out to be Poincare, so the collection of things in the kernel is in fact closed under the duality in DPR. In any case, so let me just indicate very, very briefly what goes into this proof. And in fact, I want to say that this actually holds true for not only the symmetric structure, but any of these copper greater or equal n, so in particular also for the quadratic one. But the symmetric one is the one we care about. So the first thing we have to say is, well, what is this module with involution ms? And we just define it to be m tensor over R with RS, and it turns out that this is isomorphic to m tensor over R tensor R tensor with RS tensor RS. So this is maybe a little check you have to do, but it's not terribly complicated to convince yourself that this is the case. And then in order to promote this functor that we've written down to a Poincare functor, we have to construct a natural comparison map of this sort. So from copper S mx to copper S with this m subscript s of x tensor over R rs, right? The base change of object of x. But then you just write out what these things are. So this is the mapping spectrum from x tensor x to m. This is the mapping spectrum from x tensor over R rs, blah, 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 to m tensor over R rs. And the base change functor just produces a canonical such map. Right? I mean, we just apply that on the mapping spectrum, and then you get such a canonical map. And the claim is this map is also compatible with the dualities of the two categories. So this is something you have to show. But okay, then so this provides at least that this functor is a Poincare functor, and also explains then that this subcategory is closed under the duality inside here. Okay, then something more, just a technical term that one needs to prove is that this, or maybe the following suffices, so that this kernel DPRS is in fact generated by the following objects, namely you take R modulo a fixed prime and view it as an R module. I mean, R modulo P is certainly an R module, and you view it as an R module, and these are the typical candidates which go to 0 under this localization map. So the statement is that this kernel is generated by these terms. And in fact, there is something we need to know on the underlying categories already. We need to know that this base change functor is a Verdier projection, right? Poincare-Verdier was the Verdier projection of stable categories, and together with the statement that this Poincare structure is left Kahn extended from this one. And so the first thing we have to show is that this is a Verdier projection, and what is generally true is that this is a Verdier projection up to idempotent completions, something that one might call a Karoubi projection or whatever, but the statement is this functor is also essentially surjective, and this will be enough to deduce that it's a Verdier projection. I mean, there's something one has to do, and let me very briefly indicate why this map is essentially surjective. So it turns out, to prove that this functor of stable infinity categories is essentially surjective, it suffices to prove that the map on K0 of these categories is surjective. Now, because R and RS are both Dedekind rings, it turns out that the 0th K group in both cases can be calculated in terms of a factor which is the integers determined by the rank of modules, and then some other term which is called the Picard group of this Dedekind ring. And now the definition of one definition of the Picard group for a Dedekind ring is as follows. You can look at the free abelian group generated by non-zero primes, and this receives a map from the units in K, and a group homomorphism from the units in K. And this group homomorphism is constructed as follows. So because it's a group homomorphism, it suffices to say where you send elements of your ring, because they generate the group of units in K. And so this element in your ring, you just send to X in R. Then because R is a Dedekind ring, then you can write the ideal generated by X as P1 up to R1, blah, 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 up to some other primes Pn to Rn. And so then you send this little X to the tuple Ri indexed over the Pi's, right? So in the spot, in the correct spot, you just gather the exponent of your element X, your ideal X, written as in terms of the prime ideals of your ring. So that this is where we use that we have a Dedekind ring, and every ideal can be uniquely written as a product of prime ideals. Okay, and then the statement is the Picard group is the kernel of this map, and well, then you can convince yourself that the prime ideals in this localized ring, in this ring RS, is exactly all prime ideals that remain once you remove your set S. So it's exactly the complement of S. And hence, yeah, this map will just be the projection onto the summand where you've kept these factors. Okay, so there are some things to do here, but this is sort of a general principle. And okay, so then a further thing we have to show is that this structure copper SMS is left Kahn extended from copper SM along this base change functor. And the essential ingredient to proving such a result is that A, in terms of the linear term and the bilinear term of your Poincare structure, you have a formula for the left Kahn extension. And essentially what you do is you take your module N or your bimodule M, and you just base change those bimodules, or the bimodule and the module. This is generally how you calculate the left Kahn extension. So on the bimodule level, this equation tells us that we've done the right thing. So we just take the one that we need. And in order to prove the statement for on the level of the linear approximation of our Poincare structure, the statement we have to show is really this: that if you take the Tate construction on M and you base change, it's the same thing as taking the Tate construction of the base change module. And this is essentially an instance of the fact that you can write this ring RS as a filtered colimit of three things. It's still a flat module. So you write it as a filtered colimit of three things, and then the statement is that Tate cohomology commutes with filtered colimits in discrete coefficients. So if you have a filtered colimit of abelian groups with C2 action, applying Tate C2 will commute with this filtered colimit. So again, that's maybe also not something super obvious, but there's actually a neat trick one can do to prove this result. So it turns out Tate cohomology is periodic, right? And in very positive degrees, it's group homology, and group homology clearly commutes with filtered colimits, but because it's periodic, it will commute with filtered colimits everywhere. So that's essentially sort of the steps you have to do to ensure that the extension of scalar functors gives rise to a Poincare-Verdier sequence of Poincare infinity categories of this sort. So this is a general principle of localization sequence. We just localize your ring at some away from a set of prime ideals. You obtain this guy. Just write down the kernel. It is what it is. But at least now we know that if we apply L theory, this will give you a fiber sequence by this term that I indicated in, I don't know, I think my first or second lecture of Andrews, essentially, that L theory sends Poincare-Verdier sequences to fiber sequences. Okay, So that's a good thing. So the topic of dévissage, which is the next thing we want to argue, is to get our hands on the L theory of this fiber term of the so to say S torsion R modules. What can we say about those? Okay, so this is exactly what we want to do. We want to describe this this category of S torsion R modules in terms of the residue fields at our primes, right? Remember, those were the points, the objects that generate this whole category, and in particular, R modulo P is a canonical object in here. And we want to describe this whole category at least up to L theory in terms of maybe such things, and then we have to find out what exactly, how to obtain the right quadratic functor or the right Poincare structure. Okay, so what we do is we fix just first a prime in S and consider the restriction of scalars functor now, not the extension of scale. We have the derived category of R modulo P and maps to the derived category of R. So a first exercise is to see that this is clearly well defined if you remove these perfectness conditions, right? You can just view an R mod P module via this ring map R to R mod P as an R module. And it's a little exercise to show that this is in fact well defined on the level of the perfect complexes, i.e. you have to show that R modulo P is a perfect complex itself. So that's the exercise. Show that if you have a Dedekind ring and a prime ideal, then R modulo P is a perfect R module. So once we have this, at least it makes sense to talk about this restriction of scalar functors, and what we would like to do is promote that to a Poincare functor. For this, we have to understand in general, how do we promote the restriction of scalar functors to a Poincare functor? Okay. So the proposition is in this case that the restriction of scalars functor, let me call the projection P and then this restriction functor P upper star. So it refines to a Poincare functor of the following sort. We start out with the derived category of R modulo P, and we take the symmetric structure just with respect to R modulo P. You can do something a bit more general. I don't want to discuss this today. And what we would like to compare it to is the derived category of R, now with this lower S, where S is just the set containing the single prime P, right? And if something is P torsion, then it's also S torsion if P is contained in S. So there's a canonical inclusion of that sort. And here we have to take the symmetric structure of R, but then we have to shift it by 1. That is the statement that comes out. Okay. So this Poincare functor on the level of the restriction of scalars functor will involve a shifting our object by 1s. And we will make this very explicit in a moment. And I want to say directly, so we call this, or I'd like to call this map a dévissage map, so def, but it does depend on the choice of a uniformizer pi for P. So what is a uniformizer? So the statement was still that this localization at P, Rp, is a discrete valuation ring, and such rings are principal ideal domains. So its unique maximal ideal, P, now has a generator, call it pi. And you have to choose some generator for this principal ideal. And in fact, this map will in fact depend on this choice of the uniformizer, but only up to its image in P, modulo P squared. Okay, so there's a little dependency in this dévissage map. It's not really canonical, but it is what it is. Okay, so let's first discuss how we obtain the Poincare structure on this P upper star. So what we have to provide is a map from copper S applied to an object on the left-hand side in this category. And that is given by that formula, right? It's the C2 fixed points on the mapping spectrum from X tensor X to R mod P. And what we do is we just apply P upper star and land in the R tensor R linear maps from, this term to P upper star of R mod P. And then the statement is there is a canonical map from P upper star R mod P to R shifted by 1, which satisfies the following property. So there's a general construction that is behind this. And essentially the point is that this functor P upper star admits a right adjoint. Okay, P lower star, it always exists. And the statement is that R modulo P shifted by -1 is in fact isomorphic to P lower star of R. That's just a general effect. And so you can just take the adjoint of this equivalence and stick it in here. And the statement is that the reason, I mean, if you had just a map in the correct direction, you would always obtain such a map. Then you would always obtain a Poincare structure on this restriction of scalar functors. And the fact that this map is an equivalence will guarantee, in fact, that this functor is a Poincare functor. It will be compatible with the duality if and only if this map you've chosen between these two objects is an equivalence. You don't have to understand all the details, but this is just the data we have to provide. But for now, you can imagine that it might not be so, I mean, by sort of replacing our ring R by the localization at P, we might as well for the moment assume that ring, so in other words, where this prime ideal P has a generator. And so there are two nice exercises to do, namely that prove this isomorphism in the case where P is a principal ideal, and show that that the map which is adjoint to this equivalence, which we've used here, is just the Bockstein associated to this chosen generator, right? So any such generator pi gives us a sequence R multiplication by pi R, and then R modulo P, because pi was a generator of P. And so that gives us a Bockstein map to R shifted by 1. And this Bockstein depends on the chosen generator pi. That's just a fact. And we will see instances of such a construction later. But in any case, so this is the data we will have to obtain. And at least in the case where we assume that P is principal, it's actually not very difficult to prove these equivalences, of course. And also in general, it's not very difficult, but if you have a generator of this principal ideal, it's very easy to prove these equivalences and convince yourself that this construction in fact provides a Poincare structure on the restriction of scalar functors. Okay, so the statement is, once we've chosen generators of these ideals P in the localization RP, then we can construct this Poincare functor dévissage pi, which goes from the derived category of R mod P to the derived category of R, which lands automatically in the S-Forgen complexes and is compatible once we put the shifted symmetric Poincare structure on the right-hand side. Okay, so that's the upshot. We choose these generators and obtain a restriction of scalars functor, which depends on the chosen generators and which shifts around this the copper a bit. And the theorem that we would like to prove, or which I would like to indicate at least, is that if we have a Dedekind ring and S a set of non-zero primes with chosen uniformizers pi associated to these primes, then the map that we obtain by summing up all these dévissage maps and applying L theory, this map is an equivalence. Okay? So it induces an isomorphism on all L groups. And in other words, combining with localization, we will have a localization sequence which describes the L theory of our ring in terms of the L theory of the quotient field and all residue fields that appear. This is the upshot of this game. So let me indicate what are the steps one has to take, and in the proof of this result, you will see that we don't reprove everything. What we essentially provide with this formalism is we try to reduce all statements that are around to statements about Witt groups, and Witt groups have just been studied classically just a lot, and then you can just employ results that are known in Witt groups. So the proof sketch would be as follows. The first thing is sort of formal. We reduce to the case where the cardinality of S is finite. We just have a finite number of primes, and that just works by saying everything is compatible with filtered co-limits. If you have infinitely many primes, all constructions are given by taking the filtered co-limit over the collection of finite primes. And then the second step is to say that, well, this product of, you take the product of the derived categories of R mod P, and I mean, each of these R mod P's, right, this is just the perfect derived category of a ring of finite dimension, in fact of dimension 0, right? These are all fields. So these have T structures, which are given product-wise. And the T structure is such that they send the co-connective to the connective part and the connective to the co-connective part. This really has to do with the fact that these rings have global dimension 0, right? Then we've seen, or I mean, we've argued last time that for a global dimension D ring, the duality on the perfect derived category sends co-connective objects to minus the connective objects, and if D is 0, then we're good. Okay, so the statement then is that this category of S torsion R modules also has a T structure, which comes restricted from the T structure on DPR. Now, the T structure on DPR, in fact, takes the co-connective objects to -1 connective objects only. And then it's a fun exercise to convince yourself that it turns out that this duality restricted to the torsion objects, in fact, sends co-connective objects to connective objects. Okay? That's sort of a little exercise one has to do. And you also have to check that the T structure, in fact, restricts to the torsion complexes. Right. Am I doing this right? Yes, I think so. So what we then deduce is that, so I didn't spell out that step last time, but one of the consequences that we would obtain from this general result about L theory of stable categories with a T structure whose blah, has some properties with the duality will be that the odd dimensional L groups vanish, and the even dimensional L groups are just symmetric and anti-symmetric Witt groups of the respective halves of these T structures. Just ordinary abelian categories, and Witt groups of abelian categories with duality, you can imagine, are just defined as always, right? You take objects equipped with a unimodular form, modulo things that have an actual Lagrangian. It's just defined as always. So the statement is that the L theories on the left and right hand side are concentrated in even degrees, and in these degrees they are either given by symmetric or anti-symmetric Witt groups of the hearts of the respective T structures. And now, what are the hearts of the respective T structures? Well, in this case, the heart is just the product of R mod P vector spaces, and in this case, it is given by the category of finitely generated R modules, which are also S torsion. So just the discrete R modules, which are finitely generated, and S torsion. That is what's going to be the heart in this T structure. And then you cite a result from classical Witt theory saying that a dévissage map associated exactly to you can convince yourself that the map is exactly the one that we've also constructed from the Witt group, the sum of the Witt groups of these residue fields R mod P to the S torsion modules. The Witt group is an isomorphism. And I mean, again, this is maybe not super surprising, right? Every object has a filtration where the filtration quotients are now R mod P vector spaces for a correct P. And then you sort of first show that different primes cannot interact in a unimodular manner. So you can separate all these different terms, and then for each that, you again induct on the length of a filtration or something. It's not something that's extremely surprising. But as a corollary, what you obtain is that if you have a ring R and a set of primes S as before, then you will obtain a fiber sequence sending the symmetric L theory of the ring R to the symmetric L theory of this kind of localization RS. And then you take the sum over all these, there's going to be a sum over some boundary map, which again depends on pi. And it lands into the direct sum over all L theory terms of the residue fields. So notice that the canonical fiber sequence sort of would have this on the left-hand side, but then I would have to insert sigmas here and here. So instead I take this guy here and I insert a loop on the quadratic structure, but then we know that looping the quadratic functor in fact just loops or suspends or shifts our spectrum around. So the upshot is that we obtain such a fiber sequence. takes the L theory of the ring to the L theory of the localization, and then maps to the sum of the L theories of the residue fields. Okay, so let's do an example. What can we say about this boundary map? I mean, I just want to tell you that many of these things might sound very, very abstract, but again, you can make things quite explicit. So let's analyze what this boundary map is. And the statement is, it's given as follows. So this left group, the zeroth L group of K, just in the case where we take S to be the set of all primes, right? Then you have this localization sequence with the ring itself, the fraction field, and all, the fraction field and all residue fields that can appear. And then let's focus on the summand, which is associated to a particular prime. Just look, it maps to a sum of L theories. Just look what it does to this particular one summand. And then the statement is, well, this L group we've already seen is just given by a symmetric Witt group. So these Witt groups we've seen are generated by the one-dimensional forms X, where X is in fact in a non-zero element of your ring. In general, so this proposition we had would say a non-zero element of the field. So that's given by a quotient, a fraction X modulo I, or X divided by I. But then by a change of basis, you can replace X mod or X divided by I by X times I, because they differ by a square Y squared, which you can get rid of by a change of basis. So you can get rid of all denominators by just changing a basis of your one-dimensional form. So in fact, we might assume that X is given by R modulo Rm is non-zero. Then we may assume that R is local, or else we just replace R by the localization, and the map will indeed factor through this process. So there's not going to be a problem with assuming that R is local, in which case it turns out that every element in your ring, which is non-zero, can be written as pi to the I times u for some invertible element u, right? And then again, you can assume that I is either 1 or 0, because the difference to that will be given by a square, which you don't see in the Witt group. So it really suffices to specify where the boundary map sends an element little u and where it sends a little element pi u. And then the statement is, well, u, just because it comes from the L theory of the ring, of course, must go to 0, and it does. And if you take the pi partial of the form pi times u, what you get is the form, the one-dimensional form, which is determined by u, where we view this now as a unit via this projection map from R to R of P. Okay. It's a very concrete formula. This is just what comes out. Yeah, okay, so this is, for instance, how you can describe this boundary map. And we'll actually make use of that description later. Okay, so the corollary I want to discuss is that if you have a Dedekind ring R with fraction field K, which is a global field of characteristic 2. So global in this context just means that all residue fields that appear are finite fields. I mean, that's just a short way of saying all residue fields are finite, just a global field. Then the statement is that the symmetric L theory of R is given by either a Witt group, if n is congruent to 0 mod 2, or it's the Picard group mod 2, if n is congruent to 1 mod 2. And again, the Picard group of 2 was given by some quotient. Okay, so let's prove this. This is actually quite fun and instructive to do. So just from the general theory, we have this nice localization sequence relating the symmetric L theory of R, that of its fraction field K, and to the sum of the non-zero residue fields that appear, so the R mod P's associated to non-zero residue fields. Now, if you write down the long exact sequence in homotopy groups, then you will find that those are all fields and hence have no odd L theory. Okay, and so the term that comes in from the left and the term that goes to the right, those will all be 0. And what you find is just an exact sequence of containing the 0th L group of dpr, the 0th L group of K, then the sum of these 0th L groups of the symmetric Witt groups, and then the -1st L group of R, symmetric L group of R. And of course, we've already seen earlier that for one-dimensional rings, the symmetric Witt group in degree 0 is of course the same as the genuine symmetric Witt group, symmetric L group, which we've seen to be the the Witt group. Okay. So again, we already know that L0 with the symmetric structure is in fact just the symmetric Witt group. Likewise, we obtain here that this is the symmetric Witt group of K, and likewise that this is the sum over the symmetric Witt groups of the residue field. In particular, you deduce that the map from the symmetric Witt group of a Dedekind ring to its fraction field is always injective. And that's actually a quite instructive exercise to try to prove by hand. So I mean, if you get bored or something, you can try to prove this fact by hand. Okay, but in any case, what we thus have to calculate is that this map L minus 1 of, this term, the minus first L group, it's given by the quotient of this direct sum over all these boundary maps that we had, right? And so what we have to do is we have to calculate them. And the reason that we've assumed that the fraction field is global, and I mean, where does this enter? So far we haven't used it. It tells us that all these R modulo P's are finite fields of characteristic 2. And in the exercise 5 of the first lecture, you've shown that in particular the symmetric Witt group of field of curve is Z mod 2 because the squaring map is surjective. Yeah. Right. So you've seen that these symmetric Witt groups are all just Z mod 2. And now you do the following fun trick. What you do is you write, you know that K cross, every element in K cross, the units of K gives rise to an element in the symmetric Witt group. And also you already know that the symmetric Witt group, I mean, this is K is a field of characteristic 2, so it's an F2 algebra. So this group is definitely 2 torsion, right? It's an algebra over Z2. And in other words, you can take just the free abelian group on these units, use the fact that this is 2 torsion, and obtain a map from the free abelian group mod 2 at K cross mapping to this guy. And likewise, you can take this map, and this is just the good old map that I wrote down before when we defined the Picard group, and now we take that sequence and just divide by 2 in that earlier sequence. And what we obtain is Z mod 2 free on K cross mapping to the free, so the free Z mod 2 vector space on the non-zero primes, and then the quotient will be the Picard group mod 2. Okay, so it suffices to prove that this diagram commutes and this map is surjective, and this map is an isomorphism, which we've already classified. So I now exercises to show that, well, we've made explicit what this boundary map is, so we can check that this diagram commutes, and what you obtain is that the minus first L group is the Picard group mod 2. Okay, so this is actually a statement which holds a bit more general. So, and in particular, we've understood this corollary now, right? So in fact, the co-kernel of this map from the symmetric Witt group of K to the sum over all these symmetric Witt groups of the fraction fields is always the Picard group mod 2 whenever K is a global field. So for instance, this is also true for global fields of odd characteristic or number fields. In that case, it's a bit more complicated to prove. The really helpful point was that in characteristic 2, all residue fields that appear are finite fields of characteristic 2, whose Witt group is just Z mod 2. In the other cases, those will be finite fields of odd characteristic, and the Witt groups of finite fields of odd characteristic are either Z mod 2 times Z mod 2 or Z mod 4. And then you will have to maneuver yourself a bit more complicated. It's just a bit more complicated in that case. But it is nevertheless still true. And we'll use that later as well. So, right, let's see. So that was the case of fields of characteristic, of Dedekind rings of characteristic 2 with global fraction field. And let's do another corollary of the dévissage theorem, which now deals with the case where R is Dedekind and K is a global field of characteristic not equals to 2. In this case, the calculation is a bit different, and there's another invariant that we have to take into account, namely the number of dyadic primes. So a prime is called dyadic if 2 is contained in it. And it's all the primes that divide 2. So note that this is a finite number, right? In a Dedekind ring, the statement is every ideal is uniquely given by a product of primes. So that, I mean, in the ideal generated by 2, there will be a finite set of primes appearing. You take that finite set, count how many there are, and call this D. And then the statement is the symmetric L groups of such a Dedekind ring with global fraction field of characteristic mod 2 is described as follows. The zeroth L group is the symmetric Witt group. I mean, we've seen this many times, so it's still the same argument. Turns out the first L group is Z mod 2 to the D, the D-dimensional Z mod 2 vector space. The second L group is always 0, and the third L group is the Picard group mod 2 again. And the proof of this, I don't know, I will leave as an exercise. It's you do the very same thing as here. You look at this long exact sequence, and then these steps will be formal, and for the final step, you will use this fact. I mean, this is really spelling out this fiber sequence that we had. Nothing fancy happens. And in fact, if you get rid of the global assumption, then you can still describe this term not in terms of the Z mod 2 to the D, but just the sum over all the symmetric Witt groups of the residue fields of characteristic 2. And this term just by the co-kernel of this map, right? It's just, in the case where the ring is global, these things can be further calculated. So we've just specialized down already a little bit. And to make it very explicit, let's do this for the integers. So the symmetric Witt groups, the symmetric L groups of the integers are then, as we write this as LS and Z, it's given by the integers itself if n is congruent to 0 mod 4. And in fact, one can explicitly say what the invariant is, namely you take a form to its signature. Turns out to be an isomorphism. That is absolutely not a triviality. So if you want to prove that by hand, I mean, I'd be happy to hear of an easy proof of this fact. But if you use the fact that indefinite forms over the integers are classified by their rank, type, and signature, then this is an easy calculation. But the fact that this is so is sort of, makes use of the local to global principle, a theorem of Hasse and Minkowski in quadratic forms over local fields. This is not a tautology. So in degree 1, for the integers, we're of course lucky. 2 generates a prime ideal, so it is itself already prime, and hence there is a unique prime dividing 2. So there's only one Z mod 2 summand, and the invariant you can describe as what's called the theorem invariant. It's also some explicit thing you can write down for one-dimensional chain complexes, or also in terms of formations. Or there is an explicit invariant which detects the Z mod 2. In terms of the chain complex which underlies the Poincare structure. So that's which underlies this Poincare object that you have. And then the other two terms are 0. I mean, for degree 2, that's obvious. And for degree 3, well, the integers are a principal ideal domain. You can, so hopefully it will be not too complicated to see that this map, before you've divided out by 2, this map is surjective if you have a principal ideal domain. Okay, so the statement is the Picard group of a principal ideal domain vanishes. That's of course, I mean, sort of well known. This is the concept of Dedekind rings, that you wish to understand when is it a principal ideal domain, and the first obstruction is the Picard group. So that's the one that you study. Okay, so those are then the symmetric L groups of the integers, and you can actually make, I don't know, other examples work out using this formalism. It's quite a fun game to play. Okay, very nice. So I want to finish this series of lectures with also calculating the quadratic L groups of the integers. And of course, I mean, let me say that, I mean, these calculations are not new, of course. The symmetric and quadratic L groups of the integers have been well known for a long time. But I actually have not seen in the literature the proof that we're about to give would sort of reduce everything by this sort of local to global principles to statements about Witt groups, quadratic or symmetric Witt groups of certain fields. So I'm actually not aware of. I think that's maybe a slightly different perspective just on the calculations. So the quadratic case, what happens in the quadratic case? Well, here's an exercise that probably you will not be able to solve yet, but at the end of the lecture you will. So the statement is that dévissage fails for the quadratic L theory. We cannot take this localization sequence and hope to describe the quadratic L theory of the torsion modules in terms of the quadratic L theory of the residue fields. That's just wrong. And you can write down a counterexample to that. And I would suggest for you to try the counterexample where you take Z and you invert 2. Look at the sequence you would get and see if that will make sense. So the statement is we have to get our hands at these quadratic L groups in a different manner, and the way we want to do it, or that way I want to suggest to do this, is by a collection of a couple of results that are true in this quadratic case. The first of which is quite general and applies for both the quadratic and the symmetric structure. So the setup is as follows. We just pick a ring and an element in this ring and assume that the x power torsion is bounded. That is just to make sure that some gadget that I write down is, again, I mean, here I really mean just the completion of r at x, so the inverse limit over all powers of x, like r mod x to the n. And if the x power torsion is bounded, then this is also the derived inverse limit. And really what you have to write down for this statement to be correct is the derived inverse limit. So this is just a condition which ensures that these two agree. And then for the kappa equals the quadratic or the symmetric structure, the following square is a pullback diagram in spectra. Namely, you can take the kappa L theory of R, that of R adjoint 1 over x, that of the x completion of R, and that of you first complete at x and then you invert x. Okay? So you have to assume a little bit something, namely that the map on these maps, not if you apply L theory, but if you apply K0, that these maps are surjective. Else you will have to make a slight change in what the L theory terms are. There is still a formula, but under the assumption that these map on K theory groups are surjective, then this statement is true as written. And these statements are correct if we start out with a Dedekind ring. So that's the example we care about. If you invert an element, then the map on K theory is surjective for Dedekind. And as another side remark is that if x is in fact an integer sitting inside your ring, then the same statement is true for all these kappa greater or equal to n structures that are around. In general, I'm not quite sure if that is the case. But in any case, the statement is that for both the quadratic and the symmetric structure, we can describe, hopefully, the L theory of R in terms of that where we've inverted x, or where we've completed at x, and where we've completed at x and inverted x. And okay, so how do we prove such a theorem? Very briefly. So what we write down is this diagram of Poincare infinity categories. And now the statement, sort of similar as before, the statement is going to be that these two horizontal maps are Poincare-Verdier projections. This has to do with the fact that they're given by inverting an element, and then a similar argument as before shows that these are always Poincare-Verdier projection maps. And of course, these comparison functors are Poincare functors. They're just given by the extension of scalars. That's always a Poincare functor. For these kappa Q or kappa S, one can always make these functors Poincare. And now what you just know, or what you can convince yourself of very easily, is that if you take x torsion complexes on R, then the induced functor to the x torsion complexes on the R completion, the x completion of R, that is just an equivalence of underlying categories. Because somehow, if I have a torsion complex, it is already also complete. And so I don't see the difference between all R modules and X complete R modules if I restrict myself to the X torsion R modules. In any case, so there is a general principle telling us that this map is an equivalence of underlying categories, but because this is a Poincare functor, it's also compatible with the duality, right? Because it's still a Poincare functor. But now you can convince yourself that this quadratic and the symmetric Poincare structure, they are determined by the duality. And in fact, what this tells us is that because this is an equivalence of categories and compatible with the duality, it's in fact an equivalence of Poincare infinity categories, because kappa Q and kappa S are so special. And this is exactly the reason why, in general, you will have to be a bit more careful. It might well be that this is an underlying equivalence of categories, but that the functor is not sort of an isomorphism when restricted to the Poincare structure. Okay, the identity will not be an equivalence on the Poincare structure. So that you just have to make sure, and that's a little fun fact that if you do this construction not with a general element but with an integer, then this is in fact the case.
So maybe we can discuss this later, but is the issue like some kind of compatibility with the T structure of the left vertical functor? Because you are saying that it's an equivalence on the linear part of the symmetric guy. And the linear part of the truncated guy is the truncation.
But where have I truncated something? Sorry.
If you take this kappa greater or equal than n.
Ah, yes. I mean, yes. Then the statement will be you will have to make sure that, yeah, we can discuss it later. But the statement is that you will have to make sure that, I mean, you just calculate what it means for this guy to also be an equivalence on say kappa greater equals to 0. I mean, let's just do that, and then you will find out that there is one sort of homotopy group where it's not formal that the map has an equivalence, and for that you will have to find an extra argument, and then there's I'm happy to discuss it later. It's a bit of a technical thing, but for these quadratic and symmetric structures we're in good shape. Everything's fine. So what happens is we apply L theory, and because these are Poincare-Betti projections, the vertical sequences after applying L theory now are fiber sequences in both cases. And because this is an equivalence of Poincare categories, the fiber terms are now in fact right are after theory. And now I realize that I fear my pen is running out of battery, but at the same time I cannot disconnect my my screen. So we'll just have to hope that things work out. Okay, in any case, the statement is a second result that we will wish to use as a result of Waltz, namely that if you have a ring and an ideal in this ring, and you assume that the ring is I-adically complete, then the map from quadratic L theory of R to the quadratic L theory of the quotient is an equivalence. So that's kind of the thing that in the symmetric case we have dévissage, and in the quadratic case we can use this invariance under quotients by complete ideals. That is a feature that the quadratic gadget has, which is not shared by the symmetric one. And I actually have a question. If anybody happens to know this, I wonder whether this is true if you take a Henselian quotient instead of the quotient by a complete ideal. This, I don't know. I don't know the answer to it, but it would be good if we could find out. And as an exercise, an easy exercise is just proof surjectivity for even dimensional quadratic L groups. And in fact, this works more generally if the kernel is only contained in the Jacobson radical. So the surjectivity, for instance, is true in this Henselian case. But that's sort of a fun fact to do. And as a corollary of this above construction, of this kind of theorem, one can find that if you have a ring, then there's always a pullback between the quadratic L theory of R, the quadratic L theory of its two completion, and the symmetric L theory of R, and the symmetric L theory of its two completion. And in addition, the quadratic L theory of the two completion is isomorphic to the quadratic L theory of R modulo 2 by this result of Waltz. So how would you prove such a corollary? Well, it's an exercise, so I won't say too much, but I mean, the main point is use this theorem for both the quadratic and the symmetric case, write down the canonical comparison diagram, and then use if 2 is invertible, that the map from quadratic to symmetric L theory is an isomorphism. So what comes out is exactly this pullback diagram. Okay, so let's use this kind of pullback diagram to prove something about quadratic L groups. So let's prove the following, namely that if we have a Dedekind ring R, whose fraction field is global and of characteristic not equals to 2, and again D is the number of dyadic primes, then the quadratic L groups are as follows. They're given by a quadratic Witt group in degree 0. Now there is 0 in degree 1 and Z-mod 2 in degree Z-mod 2 to the D in degree 2. So that's really just flipping around the situation in the symmetric case where it was exactly the other way around. And in degree 3, it turns out to be an extension. So there's the surjection onto the symmetric L group, and the kernel can be described explicitly as the co-kernel of, the sum of the two maps from the symmetric Witt group of R you can map to the symmetric Witt group of the two completion, and from the quadratic Witt group of the two completion you can also map to the symmetric Witt group of the two completion. And you have to take the co-kernel of this map, and this will be the kernel of this term, right? So what I want to say is that, well, we've explained what this is. This is a Picard group mod 2. And so up to an extension, we've also calculated all quadratic L groups in terms of quadratic Witt groups, the number of dyadic primes, the Picard group of your ring, and the behavior of your symmetric, essentially the symmetric and quadratic Witt theory of R and its to completion. Okay, so I mean, it's essentially all classical Witt theory groups and Picard groups that appear up to this extension that you have to solve. And okay, again, this exercise would be to prove this theorem from that last corollary, having this pullback diagram. And the hint I want to give you is that the quadratic Witt group of a finite field of characteristic 2 is isomorphic to Z mod 2. This will enter exactly in this stage. And the rest is, again, just purely formal consequences of what we've done earlier. Okay, so I suppose, maybe, let's see. I want to finish with doing the calculation for the integers. So that, I mean, you know, we can finally finish by saying what are all symmetric and quadratic L groups of the integers themselves. And okay, so what are those? The statement is that the 0th quadratic L group is given by Z, and the invariant is given by taking a signature divided by 8. So it's a good exercise to show that the signature of an even form, or of a quadratic form, so to say, over the integers is divisible by 8. Actually, also not completely obvious, but I can assure you that it's true, and yeah, there are some tricks for how one can show this. Then, of course, again, in the Z, we only have one dyadic prime, namely 2. And the invariant is the Rth invariant in this case. That's a classical invariant of quadratic forms over F2. So what you do is you take the quadratic L theory of, like the second L theory of Z, you map to the second L theory of F2. That's the Witt group of F2, and that is Z mod 2 by the Rth invariant. And now to show that it's 0 in degree 3, what we have to show is that this guy A that we have here, this co-kernel, is 0. And for this co-kernel, we just write down that we have an exact sequence mapping the quadratic Witt group of Z to the symmetric one plus the quadratic one of the 2 completion. This maps to the symmetric Witt group of the 2 adics, the 2 adic integers, and the co-kernel of this map is A by construction, right? So now it's a little fun fact or exercise as you wish to show that the map from the quadratic Witt group of Z to the quadratic Witt group of Z, the 2 adics, is in fact 0. So how do you show that? Well, we know that the comparison map going down to F2 is an isomorphism by this result of walls. And then, well, I mean, okay, so what you have to do is you pick a generator here. I will tell you the generator is the E8 form. And then you have to take that mod 2, view it as a form over F2, and calculate its Rth invariant. Okay. Statement is you can choose a clever basis or an unclever basis or whatever, but just calculate it, it turns out to be 0. So this map is 0. And this other inclusion is then by the same thing that I just said is in fact the map from Z to Z, which is given by multiplication by 8, because the A8 form has signature 8. Right? So you also know the image is exactly 8Z. So what we obtain is an injective map from Z mod 8 plus Z mod 2 to the symmetric Witt group of the 2 adic integers. And now you can do for the symmetric case, right? We have dévissage, so we understand very well what is the difference between the symmetric Witt group of the 2 adics and those of the 2 adic rational numbers. And now we're in the case of, you know, as Jonathan said in one of his lectures, the symmetric Witt groups of fields of characteristic different from 2. The fundamental ideal of these symmetric Witt groups are controlled by essentially Galois cohomology of this field. And now local fields have very easy Galois cohomology. It turns out to be controlled by these 3 groups. And from that, it's really not so difficult to see that the symmetric Witt groups of Z and the 2 adics has to have 16 elements. It's also not so difficult to compute what it is because this map is injective and the left-hand side also has 16 elements. So this map must be an isomorphism, and hence the co-kernel is 0. Okay. And I mean, there are analogs of such situations one can do. And maybe let me finally end with an exercise, which says that suppose the number of dyadic primes is greater or equals to 2, then in fact this error term A is non-zero. So in general, this will not happen, and yeah, for the integers, it is correct. Okay, so yeah, I think I've done my share of talks. Thanks so much for being here. Thanks Thomas and Artu for the invitation. I will finish here.
Okay, thank you, Markus. Yeah, are there questions about the Markus's talk today, or about the whole lecture series in general? I mean, this exercise about the signature being divisible by 8 is kind of hard, isn't it? Or is that? I mean, I always have to look up the trick. I can't.
Okay. My impression is that if, yeah, I mean, for some reason I can remember the trick. So
Okay.
but it seems to be one of these things, right? I mean, if you open up a number theory book and you just see all these arguments and all of them are super easy to follow, but I mean, how would you ever come? I don't know. I would probably never come up with it if I hadn't been told how it works. So
okay, so
it's not an easy exercise, but nevertheless, it might be fun thinking about or asking maybe what the hint is, or I mean, whatever. But
yeah, questions. Well, if that is not the case, then I think we should thank Markus again, really, for all the effort you put in. This was like a really nice lecture series. I guess it's going to be on YouTube. People can watch it again. I think it was kind of really dense on stuff to learn, so it might be worthwhile watching it again, doing the exercise in the forum. I apologize, I haven't really caught up, like answering all the great answers and sort of acknowledging the correct answers, but I will do in the next days, and we'll sort of write answers for the questions which haven't been answered. So please feel free also in the future to post in that forum. And thanks again, Markus.
thank you.